All right, finally, question number 6 of the 2016 AP Calculus exam. This is only on the AB. BC's number 6 was probably a series question. I haven't read those yet, but it's been a series question for like the last 76 years. All right, F, G, and H are twice differentiable. G of 2 equals H of 2 equals 4. Why did I write 6 here? Where did I got that? So G of 2 is equal to H of 2 is equal to 4. The line y equals 4 plus 2/3 of x minus 2 is tangent to G, is tangent to both G and H at 2. Tangent to both the graph of G at 2 and H at 2. Yeah. G and H at x equals 2. Okay, find h prime of 2. All right, well, h prime of 2 is going to be the slope of the line tangent to h at 2, and they gave us the tangent line there. The slope is just 2/3, and I'm pulling that off of the tangent line. As a matter of fact, I could have made that connection in my notes, so we already know that because this is tangent to G and H, I know that G prime is equal to H prime, and they both equal to, what was that, 2/3. All right, number B. Let a be the function given by that. Write an expression for a prime of x. Okay, so if a of x is 3x squared h of x, first we're going to find a prime of x, which is a product rule, so that'd be 6x h of x plus 3x squared h prime of x. And then I think they ask us to evaluate a at 2. So a prime of 2 is going to be 6 times 2 is 12, h of 2 plus 3 times 2 squared is also 12, h prime of 2, h of 2 is given. That's 4. H prime of 2 is your answer in part A. So if you messed up part A, you could still import that wrong answer and get full credit. So that will be 48 plus 8 is 56. You don't have to go down to the final numeric answer of 56. You could stop at 12 times 4 plus 12 times 2/3 if you would like. All right, number C, part C. The function h satisfies, okay, so h of x is x squared minus 4 over 1 minus f of x cubed, like that, for all x is not equal to 2, so I guess f of 2 is 1. I don't know. It is known that the limit of h as x approaches 2 of h can be evaluated using L'Hopital's rule. Use the limit as x approaches 2 of h to find f of 2 and f prime of 2. Show the work that leads to your answer. So if h is lopable, if you can use L'Hopital's rule, that means it is one of the two indeterminate forms, which means that find f prime of 2. Okay, which means that this would have to be 0 over 0. So if limit as x approaches 2 of h, or I lost my work. Where's the problem? There it is. Of h is lopable, solve with L'Hopital's rule, that means that the limit as x approaches 2 of the numerator, x squared minus 4, would have to equal 0, which that makes sense if you plug in 4. And the key part is that the limit as x approaches 2 of 1 minus f of x cubed would have to equal 0, because we want that indeterminate form 0 over 0, so that'll be 1 minus f of 2 cubed is equal to 0, and that means that f of 2 is going to have to equal 1. Use the limit as x approaches 2 to find f of 2 and f prime of 2. F prime of 2. It says use the limit to find f prime of 2, which I don't like. I don't know how I'm going to get f prime of 2 from the limit alone. But I do know that I could quotient rule this to force f prime into the equation. And since I know what h prime of 2 is, and I know what h of 2 is, I could work that out. I know what f of 2 is. So I'm not sure how I'm using limits to find f prime of 2. I'm going to find h prime of x as a quotient rule, which would be low d high, so that's going to be 2x times the denominator, 1 minus f of x cubed, minus high, x squared minus 4d low is going to be negative 3 f of x squared, f prime of x, all over the bottom squared 1 minus f of x cubed squared. And I could find h prime of 2 by plugging 2 into that. So it'll be 4 times 1 minus f of 2, but we know f of 2 is 1, so that's going to be 0 minus, plug in 2, we get another 0. Uh-oh. All over, oh, okay. So there's your, no? Okay, now I'm hitting I'm just brain farting, I'm not thinking very well. F prime of 2. Because h prime of 2, using that definition, h prime is undefined at 2, which, well, it's indeterminate at 2, but we're not doing a limit there. I'm just doing the derivative. If h can be evaluated using L'Hopital's rule, let's do this. Now okay, I'm gonna get rid of all that. I just had, I think it just came to me. All right, if okay, if h can be evaluated using L'Hopital's rule, then that means the limit as, geez, I'm an idiot. X approaches 2 of h of x, which is x squared minus 4 over 1 minus f of x squared, would be equal to the limit as x approaches 2 of 2x over negative, that's f of x cubed, not squared, negative 3 f of x squared times f prime of x, right? Which is going to be 4 over negative 3 f of 2 squared f prime of 2, which will be 4 over f of 2 we know is 1, negative 3 f prime of 2. Use the limit as x approaches 2 of h. Did I ever find the limit as x approaches 2 of h? I still need f prime of 2. It is known that that can be evaluated using L'Hopital's rule, so I applied L'Hopital's rule. Negative 3. Okay, I'm just brain farting. I'm going to have to stop and think about this for a minute, and for the sake of not having a terribly long video, I will pause this and I'll just let you know how long I thought about it when I come back. Okay, that took me about a minute, and I finally had my epiphany where I'm just now embarrassed that I didn't see this earlier. I did say a while ago, do we know what the limit as x approaches 2 is? And I was looking for it to be given in part C. I was just looking at the wrong part of the question. At the very beginning of the question, they tell you that h is twice differentiable. That means the function h is continuous. They also tell you that way up here, h of 2 is 4. Well, if h of 2 is 4 and the function is differentiable and continuous, that means that the limit as x approaches 2 of h of x must equal 4. So based on that continuity stuff, I now know that this thing way down here that I set up using L'Hopital's rule, that would have to equal 4, and now I can solve for f prime of 2, so that would be negative 1/3 is equal to f prime of 2, and there's our answer. So sorry that took so long, or sorry, I guess you didn't know it took so long because I paused the, whatever. All right, that was embarrassing. Let's go on and do part D. Hopefully I don't mess up part D like I did part C. Okay, shrink that up a little bit, give me some room, and let's look at D. All right, it is known that G is always less than or equal to H. On 1 to 3. Let K be a function such that K is between them. Okay, so G of X is less than or equal K of X, is less than equal to h of x. Is k continuous at x equals 2? Is k continuous at x equals 2? So, well, if k is continuous, then that would mean that the limit as x approaches 2 of k of x would have to equal k of 2. Well, we could squeeze the limit side. Do we have information to find k of 2? It is known that g and k is between those two. This one I'm not sure of. The limit part of it's not going to be bad because we already know that back up here, if g of 2 and h of 2 are differentiable and they both equal 4 at x equals 2, then we know that the limits of g and h are both equal to 2. So I would say that since h and g are differentiable, oh, that's a weird e, are differentiable, and g of x equals h of x, I'm sorry, g of 2. 4. Differentiable, that means that it's continuous. I'm all over the place now. Therefore, continuous. So since they are differentiable and continuous and g of 2 equals h of 2 equals 4, that means that the limit of g of x, the limit as x approaches 2 of g of x is equal to the limit as x approaches 2 of h of x is equal to 4. Since k is always between g and h, the limit as x approaches 2 of k of x would have to equal 4 as well by the squeeze theorem. Or the sandwich theorem, whatever you want to call it. Let k be a function satisfying that from 1 to 3. Is k continuous at 2? I know the limit as x approaches 2 of k is 4. What I'm trying to establish is, does k of 2 equal 4? And I'm tempted to say yes, because k is always between g and h, because g is less than equal to k is less than equal to h, and g of 2 is equal to h of 2 is equal to 4. And since the limit as x approaches 2 of k is 4 and k of 2 is 4, therefore k is continuous at x equals 2. I guess I'll say this again, because limit as x approaches 2 of k of x is equal to k of 2. And I'll be honest with you, I'm not 100% confident in that answer, but I feel really good about it. Anyway, all right, I'm done. I'm tired of looking at this question.